So in this short revision video, we'll look at why electromagnetic radiation is important because of how it interacts with atoms. So why do we care about electromagnetic radiation in chemistry? Well, remember what we said in the last video. When photons are emitted, given out, or absorbed, taken in by atoms, they can give or take energy from that atom, specifically give electrons energy or take energy away from electrons. So if an atom is given energy, if it absorbs a photon, the electrons move to higher energy levels. So they jump from one energy shell to an energy shell that's further away, higher in energy. We call that becoming excited or promoted. Better word is excited. So atoms and electrons become excited. Now, when an excited electron, one that is in a higher energy level than it normally would be, when that falls back down from a higher energy level to a lower energy level, that is when an atom releases a photon. So atoms themselves can give off light. So we have our photon absorbed by an atom, and what that does is it allows the electron to move from one energy level to a higher energy level. And it can move to different energy levels depending on the wavelength and the energy value of the photon. When that excited electron falls down to a lower energy level, it gives off a photon. It emits a photon. Now, the electron does not need to fall to the energy level that it originally started at. It just needs to fall to any lower down energy level to give off a photon. And depending upon what energy level it starts at and falls to, you will release a different photon. Now, every single element will release and absorb photons at different wavelengths. So what we're looking at here is the visible region of the electromagnetic spectrum. And we can see every atom has these different colored lines, and some have more lines than others, which correspond to a photon being emitted, given off. So where the lines are brighter, that's where an electron has fallen from a higher energy level to a lower energy level and released or emitted a photon. And every single atom does this differently, which then allows us to use this pattern, this sequence, to identify atoms. So why does each atom do it differently? Well, each element has its own set of energy levels that are all going to be at slightly different values depending on things like the number of electrons it has and the nuclear charge. Now, within each atom, they have different energy levels, and the excited electrons can fall to each of these different energy levels from any higher energy level. This means that you will get specific transitions, specific energy transitions from one level to another, which give off a specific photon per transition. And the different bands that we saw in the visible light spectrum in the previous slide prove that there are discrete energy levels. Now, discrete means that they exist at exact values. And because if they didn't have exact values, you wouldn't just get one line for that transition. You would get you basically get the entire spectrum. If every possible value of energy could exist for the different energy levels, you would get a photon at every wavelength possible. But we don't see that. We only see particular bands, which must mean that the energy levels exist at specific and exact values, which are slightly different for each atom. and we describe the fact that the energy levels exist at exact values that are measurable, that can be quantified as the energy levels being quantized. Furthermore, the reason we get flame tests and the reason why you can get metal gas lamps of different colours is because of these transitions. Now in this case, what you've done in a flame test is you excite the electrons using heat, and then as they fall from higher energy levels to lower energy levels, they give off particular photons of a particular wavelength, and every wavelength is going to be a different colour. What you're observing in different metals is the main transition that's happening, or for some, where you're seeing a blue and green, for example, in copper, you're seeing two different wavelengths happening side by side. Now, hydrogen is an interesting case because it only has one electron, but we see several lines in its spectrum. And this is because the electron can move between several energy levels. And now that might seem odd because if you were to draw out an atom of hydrogen, you usually only draw one energy level. The fact is, every atom has so many different energy levels that exist, they're just not occupied, so we don't usually draw them. So whenever we take a hydrogen atom and excite it, its electron can move to further or higher up energy levels. And then when that electron falls back down, we get different photons depending on which energy level the electron falls to. So, for example, we can get a transition in hydrogen from it falling from the third energy level to the first, or from the third energy level to the second, or again from the second to the first. Each one of those would give a different wavelength. And the part of the electromagnetic spectrum where we get these lines is going to depend on the energy of the photons. Now, most of the time we're only looking at the ones in the visible region, but you will also get lines in the infrared and in the ultraviolet regions. So in hydrogen, depending on what energy level electrons are falling to, there's a whole set of series. The one in the visible region that we saw on the slide 2-3 slides ago was the one in visible light, and it's called the Balmer series of lines because Balmer was the scientist who discovered them. And you can see that when the electrons fall to different energy levels, other scientists were the people who explored and found those series of lines. Now for each atom, we have a thing called the convergence limit. Now this is the point where the energy levels become so close to one another that we can no longer tell them apart, and so they converge, they come together. That's what converging means. For hydrogen, this happens at 91.2 nanometers. And this is the difference. The convergence limit is what we can consider the edge, the very end of an atom. And so if you provide energy that's greater, or a wavelength that's shorter than the convergence limit, the electron will actually be excited out of the atom and it will ionize. This is what allows us to calculate ionization energy or turn a wavelength, find a wavelength from ionization energy. The ionization energy is the energy difference between the ground state and the convergence limit. Therefore, ionization energy can be calculated from the wavelength, from your highest energy line, or if you're given the ionization energy, you could work out the frequency or the wavelength of energy needed. So in our visible light region, that convergence limit occurs at 91.2 nanometers. If we work out our energy, fill it into the equation and do it in kilojoules per mole, we get 1312. And then if we look at our data booklet, we get the exact same value. So this video has gone into how ionization energy how electromagnetic radiation interacts with atoms, we need to know that the energy levels have discrete values, giving rise to particular transitions, each of which has its own wavelength, and that normally, if we are looking at something and we're seeing it being colored, that is because we are seeing photons being emitted due to excited electrons falling from higher energy levels to lower energy levels.